Forwarding of IP packets here, when IP is used as a connectionless protocol. Okay, forwarding is based on the destination address of the IP datagram, right? That is, when IP is used as a connection-oriented protocol, forwarding is based on the label attached to the to an IP datagram. Okay, there are two types of connections possible. That is connectionless as well as connection-oriented protocol. Okay, in connectionless protocol, forwarding is based on the destination address. Initially, what the destination address will be attached to that particular packet. Based on that, this routing will be done. Whereas in the connection oriented, it is based on the label. Each packet will have its own label. Connection oriented, like switches and all, if you consider, each packet will have a label. That label in the table, the label will be considered, and a particular switch will be turned on. So we'll be studying these two concepts in this particular topic. Okay. So the first one in the connectionless protocol, destination address forwarding. Okay, so this is the traditional approach which is even relevant today. In this case, forwarding requires a host or a router to have a forwarding table. This is important. In case of destination address forwarding, okay, at each router there will be a forwarding table. Okay, there will be a table known as forwarding table, which consists information of, say, what will be the next path. Okay, it will forward a particular router may be connected to a various hosts, various devices. So it has to, the packet whichever is received at the router, it has to be routed to a particular device. So that will be taken care by the router through this forwarding table. Along with the address, it also gives the exact information like what is the interface or what is the number of hops required to move from one router to the destination. All that information will be stored in that particular forwarding table. Okay, so when a host has a packet to send, or when a router has received a packet which has to be forwarded, it basically looks at this table, at the forwarding table, to find the next hop to deliver the packet. So basically, when a host has something to send, some data to send, what happens is, from the host, the packet will go to the router. In the router, or it may be other, while receiving the data also, when the packet is arrived at the router, what the router does is, the packet will consist of the destination address. That address will be compared with respect to the table present in the forwarding table present in the router. Okay, and when the comparison, when there is a equality occurs, that is, when the address of the packet as well as in the table also if you find the same address, there for that mapping, a particular hop and a particular path will be selected, and accordingly the data will be, or the packet will be transferred. So this is the basic concept of destination address forwarding. If you consider one example, now suppose say this is the configuration given, okay, where you can observe router R1 is connected over here. Sorry, R1 is connected over here, right? Through various interfaces like say M3, M0, M1, M2, okay, which in turn is connected to various switches, correct? We can consider various hosts. Okay, each host has its own IP address. Say first one, say 180.70.65.135. Okay, followed by slash 125. When it indicates it is nothing but the masking, right? Slash 25 in the sense, as we know that overall bit size is say 32. So 32 minus 25, right? 32 minus 25 is nothing but 7. It means that the lowest 7 bits, starting from the LSB, the 7 bits, 32 minus 25 is 7. The lowest 7 bits will be appended with 0. Or else, in the other way also you can consider, it means that, say, the upper 25 bits you're supposed to consider. Suppose if you convert this 180.70.65.135 to the binary, you have to consider from the least modes. That is nothing but from the MSB bit, you have to consider the 25 bits. That will be the address, that is nothing but the address which is used for forwarding the packets. We'll study that in detail. So we, in general, we call this as mask slash 25. Okay, this is the address. Say this table, if I consider this particular block, if I consider 201 0.4, 0.16, 0.2. It is nothing but an address, and it is masked with the 22. Okay, so each block will have a masking. So masking will give us the information, like as you know that entire organization will be given a block of data, right? A set array of block of addressing will be given. So in that block of addressing, if we actually the first few addresses will be common. Okay, so this masking will whatever masking you do, say up to say 32 masking bits can be masked. What it does is it can select the full set of data instead of selecting a particular address. It can select a block of address. Okay, and the router will route it to the particular uh, host. Okay, so here you can observe the router which is connected to various hosts with a particular address as well as the masking. Okay, each has a masking, different sets of masking. So this block has a masking 26, this one has say 24, 25 and 22. Okay, now for this configuration you're supposed to prepare a forwarding table. This is the first step. When a configuration is given to you, okay, a configuration of a connection will be given to you. For that, first step is to create a forwarding table. Okay, make a forwarding table for the router R1. So how we are going to do? So this is, first say you have to list out the addresses given. Okay, all the addresses in the descending order of masking can be given, can be written first. Say first one is same address, whatever is given here. Start from 26, next it is say 25, next say 24, next say 22. The address of each host will be written here. That is nothing but network address along with the mask slash mask. Okay, it indicates the masking. It has to be written. Okay, along with that, next hop will be initially blank. It will be not known. Next is interfaces. For 180.70.65.192/26 in the previous diagram, if you mention, check out, for this particular address, network address, interface is nothing but M2. Okay, so that interface we have to write M2. So for the next address, it is M0. It will be given in the architecture in that configuration itself. For the next 201.4.22, the interface is M3. Next it is M1. Default is nothing but the address what you can check over here. This itself will be the default, that is the main router connected to the rest of the internet, that is 180.70.65.200. Okay, this is the default router. If none of the router matches to that particular address, the default router will be selected. Okay, so this is nothing but the representation. Okay, the first step, represent based on the configuration given. You have to list out the addresses. Next stop will be initially blank, and the interfacing of all the addresses you have to write. Okay, and this can be represented using bits. Okay, that is how these addresses are supposed to be represented using bits. That is basically required in order to map the receiving frame, whatever frames have been received to that router. The address will be there in that particular frame. It has to be mapped. So mapping will be done on this pages. So see, whatever you have written, say first address if I consider, which is 180.70.65.192. What you have to do is you have to just convert this into binary. Okay, if you have a calculator, just check it out. Entire thing should be converted initially. So 180. 180 is nothing but 10110100. Okay, next 70. 70 is nothing but 01000110. 65 is nothing but 01000001. And next you write 192. When you write 192, this mask plays a very important role. Okay, that is nothing but basically, as I told you, what you have to do is the overall length is 32 bit. 32 minus 26 is nothing but 6 bits, right? 6 bits you have to, the lower 6 bit, the LSB 6 bit should be appended with 0. It means the 192 will be represented with 8 bits. You are supposed to consider only upper 2 bits. Okay, only 2 bits you have to consider, or else one more simple thing, slash 26 in the sense from the leftmost, that is from the MSB, you consider 26 bits. That's all. You can observe here, this is 8, 16, right? This is the first 8 bits of 180. This is next 8 bits, that is nothing but 70. Next 8 bits, that is nothing but 65. So 8, 16, 24. Next 24 plus 2 is nothing but 26. Next 192, only the MSB 2 bits you have to consider. Okay, which is nothing but 11. Okay, so this will be the destination address now. Okay, similarly for the next one, the mask is given as 25. It means that from the leftmost, from the MSB bit, you have to consider 25 bits. So this one. Next is for 24, mask of 24. It means that from the leftmost bit, from the MSB bit, you have to consider 24 bits. You convert this everything to the binary and consider the from MSB you consider 24 bits. Okay. Similarly for the next one, it is 22 bits. Okay. Like that you are supposed to write. This is in terms of the binary, and the interface will be as it is. Okay, interfacing as per the configuration, whatever else you want, like that you have to write the interfacing part. So this is the first step. Okay, for the configuration given, you have to write the forwarding table. Okay, once this forwarding table is given, next step. So we'll continue the same question. Show the forwarding process. If now the example say show the forwarding process. If a packet arrives at R1, we'll assume that one packet has arrived to the router R1. Okay, in which the destination address is 180.70.60.40. Okay, now a packet has arrived to R1. In that packet, the destination address is given as 180.70.65.140. Now we have to show the forwarding process, how this will be forwarded to the particular host. Okay, so in order to find out the forwarding process, we have to continue from the same. First, basically, you have to, for this configuration, you have to write the table, forwarding table. Already we have written in the previous slide. A forwarding table is written, right? Once forwarding table is written, I'll assume the same forwarding table. Now we have assumed that and packet is arrived at the destination with the destination address as 180.70.65.140. Okay, what you do is you represent this 140 in binary. Okay, when I represent this 140 in binary, it gives the information as say 10001100. That is nothing but 140 in the binary. Now, how you are going to find exactly to which host it will belong? It has to be routed. Okay, so the router performs the following task. Okay, whatever address has been received, okay, it will be masked initially. In the forwarding table we have seen, if I just go back, in the forwarding table we have seen first address is this one, 180.70.65.192/26. Okay, at this order itself the process will take place. Okay, incoming packet whatever is there, it will be compared with respect to the first address. If matching occurs, then this will be the interface. Okay, if no matching occurs, it goes to the next label, next address. Here also, if no matching, next address, no matching, next address. If none of the matching occurs, then the default will be selected. Okay, now in this example, it goes with the first matching. Here the mask is /26. So therefore, the first mask is 26 is applied to the destination address. What is the destination address? This is the destination address, 180.70.65.140. Okay, so I'm interested in this last value, that is 140. It will be masked with respect to 26. Masked with respect to 26 in the sense 140 is represented in the binary as 10001100. Okay, masking 26, as I told you, you are supposed to consider the upper 26 bits, or 32 minus 26 is nothing but 6 bits, right? 32 minus 26 is 6. So the lower 6 bits should be made 0. That is 1, this 1, 2, 3, 4, 5, and 6, right? Till here, these bits will be made 0. Is it correct? It means that now overall bit will be 1000. So with what I can consider as, it is nothing but, if I consider it, it will be 128. After masking, 140 is masked with 26. Masking with 26 in the sense 32 minus 26 is nothing but lower 6 bits. 32 minus 26 is 6. Lower 6 bits should be appended with zeros. Okay, so 1 followed by all zeros is nothing but it will be equal to 128. Therefore, the result is 180.70.65 128. Okay, which does not match the corresponding network address, correct? Because actually the network address of this particular mapping is 180.70.165.192 we have to get. but what we have, the result whatever we have obtained is 128. So this address is not mapping, so it will discard this table. It goes to the next row. Okay, that is nothing but masking 25 mask will be selected. Is it correct? So it goes to the next one. The second mask is selected, which is 25. Okay, 25 again, that is 32 bit minus 25. 32 minus 25 is 7. Same process. 7 bits will be made 0. Same value I'll get, that is 128 only I'll get. So the result will be 180.70.65.128. So if I observe it in the table, 180.70.65.120. So there is a match. Okay, there is a match. So it indicates that the interface is next interface to which that particular packet should be transferred. It is nothing but the interface M0. That is nothing but from R1 through M0, interface M0, it will be sent to this host, that is 180.70.65.135. So that host it will be sent. That is nothing but which matches the corresponding network address. The next hop address and the interface number M0 are extracted from the forwarding table. Okay, is that clear? This is how the routing will take place. You'll have an initial configuration. For that configuration, a forwarding table will be developed. I hope you might have studied in the previous topics how forwarding table is written. Okay, now we have a forwarding table with respect to its own address as well as the interfaces, and whenever the packets come to the router, it will be having its destination address. Now that destination address should be masked with respect to the table, the forwarding table. In the basically in the descending order itself, it will be masked. It will be in the table also in the descending order of the mask itself. The addresses will be placed. So address by address, the mapping will take place. Wherever the match occurs, that particular what is that interface will be selected, and then the packet will be routed out. Okay, so this is for the routing will take place. So the next concept is address aggregation. Okay, if you consider this configuration, if you just check this configuration, just go through the configuration once. So here in this particular address, if you observe, here we have in this configuration, here we have two routers, right? R1 as well as R2 router. Whereas R1 is connected to networks of four organizations, right? Say organization 1 within a particular address of same mask. Next is organization 2, organization 3 as well as organization 4. Whereas R1, you can observe the forwarding table also here. R1, right? The R1 forwarding table, these are the addresses. Okay. Here the default address will be the address of R2. If none of the addresses are selected, then directly it will be sent to the router R2. That is nothing but the default addresses. These are the addresses which is related to the organizations. The first one 140.24.7.026. Similarly 140.24.7.64, like that. All these organizations are being connected with a mask of 26, along with the interfacing is also given. If you observe that R1 has a longer forwarding table, right? A larger forwarding table, because each packet must be correctly routed to the appropriate organization of R2, right? Exactly to this organization it has to be routed. On the other hand, if you just check out in R2, on the other hand, we have a very small forwarding table, right? In R2, you can observe just the network mask, that is 140.24.7.0, right? Just the initial starting address masked with 24, and the interfacing, which is nothing but F0. It has very small or very low forwarding table, right? For R2, any packet, if I consider R2, any packet with a destination of 140.24.7.0 to 120.24.7.25. Okay, if any packets with a destination is sent out from the interface M0, regardless of the organization number. right? Since here it is in general, it is given as say a point 0/24. Any packet, this is nothing but a block of data, right? A certain block has been selected. Any packet in that address starting from 7.0 to 7.25 will be sent to the organization number. This is known as address. This is called as address aggregation, because the block of address for four organizations are aggregated into one larger block. Is it correct? Here, in this particular table, this is nothing but a block of addresses. Okay, whatever four addresses we are given for the aggregation, the organization, it has been considered in the single block here. Okay, it has been aggregated in the single block. Any message if you want to transfer at this particular address will be forwarded to the entire organization. So all the addresses, it will be forwarded, and this process is known as address aggregation. So R2 would have a longer forwarding table in each organization had address that could not be aggregated into one block. Okay. Next is longest masking. Okay, longest mask matching. Here, if you observe what happens in this particular configuration, if you observe, okay, what happens if one of the organization in the previous figure, here if you, in the previous figure we had four organization. Now in this particular configuration, one organization has been placed in the router 2. That is, say organization 4 has been placed in the router 2. Right, from router 1 it has been placed in the router 2. So whether we can still use the same idea, still use the same, say, address aggregation block can be used. Yes, it can. We can use that same concept, because routing in this particular addressing, it uses the principle that is longest mask matching. See, if you just go through the table, now the table has been updated. In this particular table of router R1, we have only three addresses of the organization. Three organizations are there, that is 7.0, 7.64, and 7.128, right? Along with that, one organization has been shifted here, that is 140.24, 7.192, and here this addressing is done. So this is this concept, that is longest mask matching. This principle says that the forwarding table is sorted from the longest mask to the shortest mask. That is what I told you in the previous table also. While you sort the table, while you place the table, always the longest mask will be placed first, and then the shortest one will come to picture. So whenever what happens, whenever the frame, a particular frame with a particular destination comes near the router, okay, it will be always masked with the longest mask first. Is it correct? Say first, say 26 minus 32 is 6 bits. Lower 6 bits will be appended by 0. So it will mask with the longest mask. Okay, longest mask first. So if there is equality, then directly the packet will go to this organization. If this particular address is not equal, then it goes to the next address. Then the masking will take place with respect to 24. Here, this is nothing but if the matching occurs here, this is aggregation what we have seen in the previous. Then that particular packet will be sent to all the organizations starting from 7.0 to 7.25 address. In that, whatever hosts have been connected, so that the packet will be sent. So basically, in the longest mask matching, what the concept is that the masking, the address will be placed on the sequence as which has the longest mask first. Okay, so accordingly, the forwarding table will match the incoming packet, and based on that, the transmission will be done. Okay. So that is the one concept. The next concept is hierarchical routing. Okay, to solve the problem of gigantic forwarding table, like as the number of hosts increases in the router, obviously the table size will also increase. So in that case, again, the mapping, whenever a particular packet comes, mapping should be done. It will also, the time required for the mapping will also increase, right? So in order to avoid it, we can create a sense of hierarchy in the forwarding tables. That is, internet will be divided. So whatever internet will be there, it will be divided into various categories like backbone and national ISPs. National ISPs, first internet, main internet will be divided into national ISP. Next, national ISPs are divided into regional ISP, and again regional ISPs are divided into local ISP, right? Local ISP based on the organization, it will be divided into various sections, right? Hierarchically, this division can be done. You can observe that. Say this is a regional ISP to the rest of the internet. Okay, it will have its own IP. So this again will be divided into local ISPs. Okay, various local addresses will be given. You can observe this masking. Initially, this is 120.14.64.0/18, right? So total of 16,384 connections can be possible. So here it is 120.14.64.0/20. Like that, various connections will be given to the local ISPs. Okay, where you can observe total of 4,096 connections are possible. Whereas again, a local ISPs again it can be divided into small ISPs. Okay, again the mask will be increased. Again, the small ISPs can be given to the organizations, right? Like you can large organizations or the small organization or to the particular user itself, it can be given say on 20.14.64.0/30, like that various type. This is how hierarchically the entire system can be divided. Okay. Next topic, the second type in the connection, as we have discussed in the first slide, there are two types of connection. One is connectionless transfer, and is connection oriented. The connectionless is nothing but based on the forwarding table. This packets will be transferred, which we have discussed in the last PPT. And next one is based on the uh, connection oriented, which is nothing but forwarding based on the labeling. Okay. In 1980s, an effort started to somehow change IP to behave like a connection-oriented protocol in which routing is replaced by switching. Now, instead of routing, we have switching, which is nothing but connection-oriented protocol network. Okay, in a connection-oriented network, what is nothing but a virtual circuit approach, a switch forward of packets, okay, based on the label attached to that packet. Each packet will have a label. Okay, that label will be mapping to a particular switch. So the switch itself will forward that packet. Okay. Here, the routing is normally based on searching the contents of a table, right? In the routing, in the last concept, in the forwarding table, what we are going to search in the table, right? Whereas switching can be done by accessing a table using an index. Here, each table in the switching, each table will have an index. Okay, that same index will be present in the packet also. So based on that index mapping, here the transfer, the routing or the transfer of the packaging will be done. Whereas in other words, routing involves searching, switching involves accessing. Okay. So this just an example. So forwarding based on the label. So here forwarding, it is based on the this is nothing but an example of the forwarding table. The previous example, say when a packet arrives, okay, to a router. This is a packet. This is nothing but the address of the packet. Some value is there. So what that address, whenever it comes to a router, that router will be connected to various hosts. Now we have to decide at this router to which host, to which particular interface you are going to send the packet. So when a packet arrives at the router X, this address will be given to the forwarding table, right? This address will be given to the forwarding table. Here you can observe mask, mask. In this particular example, you can observe say mask. It is nothing but the table which we have seen in the previous PPT. It will be arranged in the form of a descending mask, right? Because this address will be masked with respect to 32. Okay, if the network address is equal, if it is equal, then next hop will be selected as well as the interface will be selected, and then packet will be forwarded. If it is not found, goes to the next mask, like that goes to the next address, next address. Say in this case, at the 30th mask, this network address are equal. After masking, if we find that network address is equal, then the packet will find its next hop address as well as the interface address. In this example, it is given as y and 2. It means that from the router, it will go through the interface 2. Okay, go through the interface 2 with the hop. The number of hops required to reach the destination will also be placed. That is, x is the destination address, y is nothing but the number of. Okay, so based on that, it goes to the destination. This is what the forwarding table is. Now, the labeling, what the labeling is, okay, this is an example for forwarding based on the label. Okay, say here the whatever packets come to the switch, okay, will have an index, will have a number. Okay, that is nothing but we call it as a label. Here in each switches we have a something known as switch table. Okay, in the switch table basically this indexing will be continuous number 0 1 2 3 4 5 6, like that continuous number will be there, and in that index there will be two information. One is interface, same information, that is interface, as well as the next label. Instead of hop, in the previous case we had in the forwarding table we had a number of hops. Instead of hops, we here what we have is one is interface, and along with that the next label will also be added, because when it reaches to the particular, maybe sometimes from router to router the connection should be done, or router to host the connection should be done. So the next label, say here 4, directly it goes to the label which is indexed as 4. Okay, and in that whatever is there, that is 2, is nothing but the path, interface path. This particular switch will be selected and the frame will be transferred from a switch to the interface 2. Along with that the next label address will also be placed here. Initially, before the switch, it was 4, and after it has crossed the switch, from here the data has been accessed, the next label address has been accessed, and that will be placed in the label. Okay, so this is known as accessing method. In the previous, forwarding is nothing but it is a searching technique. Okay, where based on the mask continuously one by one we are going to search. Whereas here we don't search based on the label, directly we'll go to that index, label index, and in that we have interface number as well as the next label data will be there, that will be placed to the frame, and then the packet will be transferred. Okay, this is about forwarding based on the label. Along with that, this label will consider various, it has its own protocol also, that is nothing but multi-protocol labeling switch. Okay, so this is the overall, what do you call, the frame, or overall contents present in the frame of the labeling. Okay, label switching. So which consists of IP payload, along with that it has IP header. Okay, along with that it is nothing but MPLS header, that is multi protocol labeling switch address. Okay, which in turn you can observe here this MPLS header, in the internal structure of LPLS header it is given here. Okay, which is nothing but you can observe it is again 32 bits. This is nothing but a table, a stack of labels, a stack where you have various labels. Next, EXP. Now we will discuss what is EXP, what is S, and what is TTL. Okay. Okay. Now, in this particular case, if you observe, the MPLS header is actually, it is nothing but a stack of subheaders that is used for multi-level hierarchical switching. Okay. So what is this? What do you mean by label here? The label, it is nothing but you can observe here. Okay, see this is the overall frame. First, initially it has got IP header. Okay, and nothing but all that information of source or destination, all that will be there, as well as the IP payload. Along with that, this is MPLS header. This is the main header which is used for the switching purpose. This header, again, the internal structure of this header is given here. Is a stack like structure. Okay, this label, it is, you can observe, it is 20-bit wide field. That label is used to index the forwarding table in the router. Okay, this is nothing but it acts like index. Initially this is 0, next 1 2 3 4 5 6, like that it continues. Okay, this it acts like a indexing for the forwarding table. Okay, along with that the next information, that is EXP. This is a 3-bit field. EXP is a 3-bit field which is reserved. Actually it is not used, it is reserved for the experimental purpose. Okay, next bit is nothing but a single bit, it is nothing but yes. So this one bit we call it as a stack field. Okay, yes is nothing but a stack field that defines the situation of the subheader in the stack. Situation of the subheader in the sense, when that bit is 1, it means that header is the last one in the stack. Okay, out of this if suppose say that it is pointing to the last label, if it is the last header, then this S will be set to 1, or else it will be set to 0. Okay, next one is the TTL. TTL is nothing but 8-bit field. Okay, this is 8-bit field. It is similar to TTL field in the IP datagram what you have studied. Okay, now each visited router decrements the value of this field. When it reaches 0, the packet is discarded to prevent the looping. That is nothing but basically some value will be placed here. TTL value will be placed here. So whenever this packets goes to the router, okay, from router it will be again moved to a particular maybe a router or a particular host, whatever it is. So every time when it goes to the router, this TTL whatever value has been loaded earlier, it will be decremented. Okay, it will be decremented by 1. So it means that until the TTL value goes to 0, the packets can be routed. Once it goes to 0, the entire packet will be discarded. Okay, so this is about the overall fields present in the switching of any particular device, or in the sense that is nothing but label switching. Okay.